In recent years, while riding in my vehicle, I was rear ended on two separate occasions by other drivers and their cars. On the one occasion, the entire back end of my vehicle was smashed up. It had to go to the shop and get repaired. I didn't have it for a whole month, and it was just really wrecked. On another occasion, the driver hit the back end of my vehicle, but did it so lightly that there was actually no damage at all. And that's a good analogy for what we're talking about in this video. Ladies and gentlemen, welcome to this video. This is AP Chemistry Section 5.5, all about collision theory. But here we're talking about collisions between molecules. In this video, we're going to find out what constitutes a successful collision. We're going to look at a couple of diagrams, and we have 6 questions, very similar to questions you're likely to see on your exam. So grab a pencil and let's get started. Here are our learning objective and essential knowledge statements for this episode. The learning objective is to explain the relationship between the rate of an elementary reaction and the frequency, energy, and orientation of particle collisions. For an elementary reaction to be successful and produce products, reactants must successfully collide to initiate bond breaking and bond making events. In most reactions, only a small fraction of the collisions leads to a reaction. Successful collisions have both sufficient energy to overcome the activation energy and orientations that allow the bonds to rearrange in the required manner. The Maxwell-Boltzmann distribution, here it is again, curve describes the distribution of particle energies. This distribution can be used to gain a qualitative estimate of the fraction of collisions with sufficient energy to lead to a reaction and how that fraction depends on temperature. Okay, so we hinted at collisions in our last episode on elementary steps. But again, for a molecule to react with another molecule, they have to collide. They can't do it from across the room. And in any sample, you have molecules colliding with each other, sometimes more, sometimes less, depending on the concentration and maybe the temperature. But there definitely needs to be collisions. But unlike the case of automobile accidents, we actually often want these collisions to occur. Okay, so a repeat slide from last time. We have two reactants, NO2 and CO. Basically, they have to collide. They make sort of this middle transition state where they're not quite products yet, but they're not reactants anymore either. And that's a high energy situation that happens during the collision while they're interacting. Okay, and we also mentioned last time that successful collisions, in order for the molecular collision to be successful, the molecules must collide with enough kinetic energy to overcome the activation energy and collide with a favorable orientation that allows transfer of atoms from one molecule to another. All right, let's talk about that kinetic energy. Here's a diagram showing a bunch of particles with varying energies moving randomly. And I show this to you because you're likely to see pictures, diagrams like this on an AP exam or your exam, where there's little arrows coming off of these particles. And those little arrows are trying to represent maybe what kind of speed or kinetic energy they have. So something with a longer speed would be moving faster, something with a shorter arrow would be moving slower. And we could imagine maybe two of these slower particles bumping into each other and not much happens because they're just kind of like going really slow. But if something like this one goes in there and slams into something like this one, they might do so with such a great force that they transfer atoms, they transfer electrons or protons or whatever it is they're doing, and we get a reaction out of it. We talked about maybe a good orientation, but again, all three of them not doing that. All right, let's talk about kinetic energy. Just like last time, if two molecules collide with not enough kinetic energy, they will just bump off each other and that's it. They will go on their merry way. But if you get a lot of kinetic energy, they can react and transfer something to the other. So a little bit of repetition there. Let's take a look at this graph. Hopefully you've seen one of these before. We've seen them in previous videos as well. But this is a Maxwell-Boltzmann distribution for some sample. All right, and what is it trying to show us? The number of molecules with a given energy, here's where the most of them are, and the actual kinetic energy down here. So they show us that, for example, at temperature number 1, there are a few molecules that have very little kinetic energy, like those ones with the little arrows. There are some molecules with big arrows, and they're going to be moving fast. The vast majority of them are somewhere here in the middle, near where the average kinetic energy would be. And that would kind of dictate the temperature at which this sample is at. But if I were to increase the temperature, this entire mountain gets shifted over a little bit. The area under the curve is going to stay the same because it's the same sample of molecules, but the mountain got shifted to have a wider base and a lower altitude for the peak. Okay. And that, because that peak moved to the right, it's showing me a higher temperature. But notice over here, there's a line that's been drawn. And that line is often drawn on graphs that you're going to see. It's a line that represents the minimum amount of energy that's required to react. Like how fast do those molecules have to be going? How much energy do they have to have? There's a minimum, and that line represents the minimum. Notice that in our second graph at the higher temperature, a greater fraction of the mountain, greater fraction of the area under the curve is past that line. And so at a higher temperature, there is a greater fraction of molecules, and so the reaction is going to probably happen faster because now you've got more molecules who are able to do the reacting. And this is very commonly seen on AP exams and other exams, and so you want to be aware of it. Likewise, if it goes back to the left, we lower the temperature, you'll have less molecules with the amount needed to react. Okay, I have 6 multiple choice questions here. 3 of them I'll do with you, and 3 of them will be pause the video moments real quick. So which of the following best explains why the rate of reaction increases when there is an increase in temperature? So we've got, at higher temperatures, reactions have a higher activation energy. At higher temperatures, reactions have a lower activation energy. At higher temperatures, high energy collisions occur more frequently, or at higher temperatures, every collision is successful. So this goes back to our graph. Notice that when the mountain shifted, this line didn't change. That didn't shift left or right. The activation energy stays constant. They just need that certain amount of energy. Unless you add a catalyst which changes the activation energy, this is going to stay constant. So that rules out questions 1 and 2, or choices A and B, and leaves us with choice C. At higher temperatures, high energy collisions occur more frequently. All right. Not every collision is successful, even at that higher temperature. Only a small fraction are above the line, but letter C is our choice there. So a similar question coming up for you to pause the video. This is a 3-part question. Take a moment and see if you can find the correct combination of factors that affect the rate of a reaction. Pause the video. I'll see you back here in a second. And if you chose all 3, congratulations, you were paying attention. The orientation of reactant particles does matter. The kinetic energy of the reactant particles does matter. And the frequency of those collisions between the reactant particles, that matters too. So that will all affect the rate of a reaction. Now let's take a look at this question, which is a very visual type of question. It says the reaction between PO3 and PO is represented by this equation right there. Which of the following best shows a successful collision? Phosphorus being the dark one, oxygen being the light one. And what we have to do is, when you see a question like this, you have to look at the equation and see what is being transferred from one thing to the other. Okay? And I can see that this PO3 starts with 3 oxygens, but only ends up with 2. So one of these oxygens has to go from this to that. And that means we have to have a collision where the oxygen is the one hitting the other one, hopefully in the appropriate place, maybe a phosphorus, so that it can attach to the phosphorus, not the other oxygen. So I would look around here for a PO3 in which one of the oxygens, these white ones, is maybe pointing toward one of the other ones. And I see a couple candidates, A and D here. Now in this one, the oxygen would hit the other phosphorus. In this one, the oxygen would hit the other oxygen. So I'm going to pick A because I read the equation, I found out what was being transferred, and gave that atom a chance to be colliding with the other appropriate atom over here. So you really have to, it's an exercise in visual, understanding of the atoms and the orientations that they have. So take a look at this one, and we'll pause the video here as well. We have 2 possible combinations. The collisions above might occur during the following reaction. There's your reaction. Which of the following best represents an ineffective collision this time? So take a moment, pause the video, and see what you think about the answer to this question. Okay, so in our reaction, an oxygen has to go from the NO2, that's this guy, over to the CO. So we need the oxygen to be pointing toward the CO if it's going to happen. And in this case, I see that it probably would combine with the carbon. And if it has enough kinetic energy, it might transfer that oxygen. But over here, the oxygens are pointing away from the CO, and that would be being hit by the nitrogen. That's probably not going to be an effective collision because if we want to transfer an oxygen, they're on the wrong side of the molecule. So the ineffective collision is diagram 2 because the oxygen atoms will not collide with the carbon atoms. So if you got that one, great, you're mastering this whole idea. My last 2 questions have Boltzmann distributions on them. So we'll do one together, and that's this one. The diagram above shows the distribution of molecular speeds for equimolar samples of a reactant. So these are all the same reactant, just at different temperatures. Which of the curves represents the temperature at which the reaction has the slowest rate, and why? So if I'm thinking slowest rate, that means less effective collisions. Maybe the molecules are moving slower, maybe they don't have the right orientations, but since this graph is showing me molecular speeds, I got to think about the slower part. And I'm going to go with peak number 1 because that represents the lowest temperature. And the lower temperature, the slower the molecules on average, and you got a smaller area under the curve that is beyond the activation energy. So that's T1. And here's one for you to try. Here's another Boltzmann distribution of the SO3 molecules in the following reaction. Which of the following best explains why the rates of reaction are different at temperatures 1 and 2? Take a moment, pause the video, and see about your answer to this. Okay, I can see that at temperature 2, sorry about that, we have shifted to the right, so it's a higher temperature, a higher area under the curve past the line. So temperature 2 is a faster rate, and that's because a greater fraction of molecules have the minimum energy required for that reaction. So if you pick D, congratulations. Now, I know a lot of you are super, super smart, and you're also super, super curious and wondering, how is it that we even know what this activation energy is? We can't even see those molecules, and we can't see their individual collisions, and there's no like little mountain of energy that we can see. Well, thanks to a guy named Svante Arrhenius, we have an idea of how to find the activation energy for a reaction, and we'll get to that in our next episode. Hope you found this episode helpful. If you have questions, leave them for me in the comments. And in the meantime, happy studying and have a great day.